Hi everybody. I'm sorry that you weren't at school today. It could be any number of reasons. Maybe the smoke got to you. Maybe you didn't feel well. So anyway, I wanted to make this video covering the most important parts of the lesson that we covered today. Today was all about direct instruction. So what I did was I just stood up in front of the class and I taught. There was no pair sharing. There was no anything other than me delivering a lesson. So that's what we're going to do here. So in this section, can we do this? What's acceptable? What we did was we explained what moves were made. Remember, we're talking about, what are some of the legal moves? We talked about this last week. So let's take a look at the first one. 16 is equal to 4 times the quantity of 9 minus x, and 16 is also equal to 36 minus 4x. So I want to know, what moves were made in order for me to go from here to here. Well, over here, what I did was, I know that I used the distributive method. So I'm going to write distributive method, and when I do that, I know that I am going to multiply 4 times 9, and I'm going to multiply 4 times negative x. So this is what I'm doing. 4 times 9, which is 36, and 4 times minus x, which is negative 4x. So these two are definitely equivalent. Yes, it's acceptable. We can do this. Moving on to number 2. I'm going to notice that I have 5x is equal to 24 plus 2x, and I got to 3x is equal to 24. So what was the move that happened? Well, we subtracted 2x. So if I do that, just right here, if I subtract 2x from this side, that means I have to do it to the other side. And if I do that, I know that 2x minus 2x is 0. And then what am I left with? I'm left with 3x is equal to 24. So this comes on down. And yes, it worked. And what did I do? I subtracted 2x. Looking at the next equation in my table, I have 5x is equal to 3 minus x. And I want to know, can I make this move? What happened? Well, I used the commutative property. So what I did was I actually moved this minus x to the front, right there. And I need to remember that when I have just a number, 3 or 5 or 10, then I never write this, but there's a little positive sign in front. That's why I'm able to write plus 3. So I use the commutative property. I think commutative. It's got 2 m's in it. So I use the commutative property to move the x to the front, and I put that subtraction or that negative x in front there. So this definitely works. I can do that. Okay, moving on. I'm going to look at this next one. This next one says 9x is equal to 5x plus 4. And I'm going, okay, what'd they do? Oh, well, I could see all the x's are on the left side. So how do I move this over here? Well, in order for me to move it, I need to subtract it. It says subtract 5x, subtract 5x. Well, when I subtract those, I'm left with 4x. And is equal to 4. So this can't happen. This was not, the move was not correct. So I'm going to write not correct. Okay, so then the last one, I'm going to look at this, and it's going to say, okay, well, I've got negative 11 times x minus 2 is equal to 8, and x minus 2 is equal to 8 plus 11. So I'm looking at this move, and I'm going, what did they do here? I have plus 11 right there. So if I add 11, well, that's how they got the plus 11 and the 8. But this is not a legal move. it can't happen. So, and the reason why is I'm not subtracting 11, I'm actually multiplying, so I would be using the distributive property. So this is not a legal move. Can't happen, therefore these are not equivalent. So this one, and this one, these are all equivalent. So I'm going to write equivalent. So I did kind of a legal move to make them equivalent. Alright, moving on, turn the page. The next page, you're going to see that we're looking at a couple of different equations. And right up here, we've got Noah. So Noah is having some trouble. He's solving two equations. He took steps that he thought were acceptable, but he ended up with statements that are clearly not true. And let's just take a look here. So I could see why. Look at, he's saying 6 is equal to 1. Right? So we're going to analyze his work and look at the moves he made. Were they acceptable? Why do you think he ended up with a false equation? And we're just going to talk about it. So let's take a look. So I've got this original equation. So his first move was he applied the commutative property. So you could see that he moved this close to here, and he was able to put those together, and then he combined like terms, which got him to x, and you have plus 1, and then we have x plus 6. So I don't see anything wrong yet. Then what did he do? He took x away. He subtracted x from each side. Totally okay. That's a legal move, because we typically solve for x. But I want you to look back here. And let's just talk about equivalency for a minute. Is it possible for me to have x plus 6 equal to x plus 1? Is that even possible? So if I put a value of x in, that x has got to be the same value of this x. Well, I can tell you right now that it's never going to be equivalent. So this is just an equation that has no solution. And that's no solution. And that's okay to have an equation that doesn't have a solution. You didn't do anything wrong. Noah didn't do anything wrong. He made all the acceptable moves. It just didn't work out. So that's a possibility of having no solution. Okay, moving on and looking at number 2. Again, we've got an original equation. You could see that he applied the distributive property. So he multiplied 2 times 5, 2 times x, which you got right there. And then he's got so he put those, that's right there, and this is the same. So then he subtracted 10 from each side. Totally okay. He can subtract 10. And if I subtract 10 from 9, I get minus 1. So I agree with that. Okay, so now what did he do next? He added 1 to each side. Add 1, add 1. Totally okay. So now take a look here at what I've got. So I've got this 2x is equal to 3x. Well, and 2 is equal to 3. So he divided both sides by x. Well, that's okay because, well, what would we have wanted to do? We would have wanted to move all of these 3x's to this side. So what would I have done? I would have gone 2x minus 3x. Okay, and what do I get? Well, if I take 3x away, I get 0, right? All right, well, combine these. So if I combine them, I get negative x is equal to 0. Therefore, x is equal to 0. So where did he go wrong? Well, he went wrong by dividing each side by x. We would normally move this entire thing over to get all the variables on one side. The only thing then, but I really want you to use some logic here. I want to go back to this. 2x is equal to 3x. What value of x? First of all, I look at this and I go, well, if I try to put in 1, 1 doesn't work. If I try to put in 2, 2 doesn't work. So basically, what value of x will work? Well, x is equal to 0. So this could be a solution. So x being 0 could be a solution. Okay, so let's recap. What do we know? So if I go up here, if it doesn't work, so take a look in number 1. It didn't work, right? So what happened? No solution. Number 2, well, it worked. I just have x is equal to 0. So if it doesn't work, going back to my original equation, right up here, my original question, it doesn't work. What does it mean? Well, it means that I could have no solution. It's totally okay. And I could have where x is equal to 0. Those are two viable options or viable things that I can state in a linear equation. I want you to be okay with that. Okay, so now we did was we went on and we looked at 8.1. And 8.1 has a table, and the table shows a relationship between a base length b and the area of some parallelograms. Okay, so let's draw a parallelogram. Here's a parallelogram. Okay, and this table represents the parallelogram's base in inches and the area. And it's telling me that all the parallelograms have the same height. So that means this B is the base, and I'm measuring that in inches. And I've got the height right here, and the height is the same for every parallelogram I draw. And the area, which is the space inside this shape, is going to vary depending on what my base is. So we know the base length is measured in inches and the area is measured in inches. And it says go ahead and complete the table. So I'm going to look, and if my base is 1 and my area is 3, well, what is my height? Remember, it's the same every single time. So I need to remember that area is equal to base times the height. Okay, so B times H. So if my base is 1, what do I multiply 1 by to get to 3? Oh, I multiply it by 3. And remember what it said. It says that all parallelograms have the same height. So that means my height for every single one of these should be 3. So if I multiply everything by 3, then I can fill in the rest of my table. Well, for my table here, I know that 3 times 3 is 9, 2 times 3 is 6, and 1 times 3 is 3. Well, now I've got to do the math of 3 times 4.5, and I used a calculator, and we got 13.5. And then what I did was I multiplied 11 over 2 by 3, and I got 33 over 2. And if I simplify that, that ends up being 16.5. Okay, well now I've got the rest of this table to fill in. But now I'm given the area of 36. Well, if I work backwards, if I work in this direction, instead of multiplying by 3, I would divide by 3. Therefore, I know 36 divided by 3 because the inverse operation of multiplication is division, so that's 12. And I could do the same thing here, divide by 3. Well, if I have 46.5, and if I divide that by 3, I get 15.5. All right, so I filled in my table. So now, what they're asking me to do is, I've got this relationship up here where base times height is equal to the area. Well, now we have to decide whether each equation could represent the relationship between B and A. Well, I could do this one or two ways. I can select values from my table and I can plug them in, or I could take a look and go, okay, well let's take a look here. They're saying that the base is equal to 3 times the area. Well, let's just see if that's true. That means the base is equal to 3 times this. Well, that doesn't seem, because then my answer would be 9. So let's just plug it in and check. I'm going to use the values of b is equal to 1 and the area is equal to 3. I'm just going to be really straightforward here. Okay, so I'm going to use that for each one. I'm going to go 1 is equal to 3 times 3. Well, we already know that doesn't work. This could not represent the relationship because the base is not 3 times the area. The base is 3 times the height, or the base is 1, the height is 3 times bigger than the height. Okay, so let's look at this one. This is saying the base is equal to the area divided by 3. Well, take a look right here. Did we not take the area and divide by 3 in order to get the base? Absolutely. And I could double check my work by taking the base of 1 and making it equivalent to 3 over 3. Well, that most definitely works. And I could keep doing the same thing. Well, they're saying that the area is the base divided by 3. So if I take the base and divide that by 3, I get 1/3, so that's not going to work. But I'll verify it. I'm going to say 3, which is the area, is equal to 1 divided by 3. Well, no, doesn't work. I already knew that. Okay, this last one says area. So I'm going to use area is 3 times the base. The area is 3. There it is. Here's the other one. Works. And I can verify it by putting the area of 3 in. And I know that it's 3 times 1. Okay, so I'm going to look at these two that work. And I'm going to write them over here. Base is equal to A over 3, and the area is equal to 3 times the base. So I want you to solve. So take a look here. What would happen if I tried to solve for B? What would I need to do? I would need to divide by 3, which means I've got B is equal to A divided by 3. These two are the same. I've just manipulated the equation to be equivalent. I've taken this equation and I've manipulated it to solve for B, which is what we are going to do next in our final activity. And I'm going to skip page 4. I did not do page 4. We are going to look at page 5. And this is where we're going to end. We are going to end by manipulating and solving for a variable to make it easy. So take a look. When I solve for a specific variable, it is an efficient way to find values. Efficient. Meaning I can do it quickly. So if not, I've got to plug numbers in, do my arithmetic, and make it work. And let's just take a look at this problem, and I'll show you what I mean by that. Okay, so I have an example of an elevator. This is a freight elevator. And this elevator has a capacity of 3,000 pounds. And it's being loaded with boxes of 2 sizes, small and large. Okay, and we're told that a small box weighs 60 pounds and a large box weighs 150 pounds. Okay, so small, 60, large, 150. Okay, they're telling us that they want X to be the number of small boxes and Y needs to be the number of large boxes. And we can represent this combination of small and large boxes that's going to fit into this elevator by writing the following equation. 60x plus 150y equals 3,000. So remember that x is the number of boxes and small boxes, I should say, sorry, and y is the number of large boxes. Okay, what else do I know? 60 is pounds. This is how much it weighs. Okay, and 150 is how much a large box weighs. Okay, and the 3,000 is the capacity. I cannot go over the capacity of the elevator or I'll have a problem. Okay, so straightforward, it's telling you, okay, if I have 10 large boxes, how many small boxes could I load? Well, what do? I'm going to take the 10 and I'm going to plug it in where the large boxes go for y. So I go 60 x plus 150 times 10 is equal to 3,000. And I'm going to go ahead and continue to solve and simplify. I got 1,500 is equal to 3,000. I'm going to do a legal move of subtracting 1,500 from both sides. Alright, so I do that, and I get 60x is equal to 1,500. Okay, now another legal move would be to divide by 60. Alright, divide by 60. And I get that how many small boxes could I actually load into this freight elevator? I could load 25. So x is equal to 25. What does that mean? That means I could put 25 small boxes in the elevator with 10 large boxes. Okay, well, now my boss, so I'm trying to do this for my boss, and now my boss says, well, isn't there another, like, I want to know if you can fit 60 large boxes in there. That means I got to go and do that math all over again. Okay, well, I'm going to do the exact same thing. I'm going to go 60x plus 150 times 16 is equal to 3,000, and I'm going to go through the same method, and what I'm going to end up doing is I'm going to find out that x is equal to 10 small boxes. Okay, well, he keeps asking me how to do, oh, well, now I want 9 large boxes. How many small? Oh, my goodness. Well, this is just really an inefficient way to do this. What I could do is, couldn't I first just solve for x? And if I solve for x, then I know that the number of small boxes, anytime I plug in, of course. So let's go ahead and do that. So on this back page, what we're going to do is I'm going to take you through the legal moves to solve for x, because we want to be efficient. So we're going to solve for x. So that means I'm going to rewrite this equation, 60x plus 150y is equal to 3,000. Okay? And I'm going to, again, solve for x, so that means I'm going to get this guy all by himself. So what is my legal move that I do? Well, I'm going to subtract 150 from both sides. And I'm going to bring the y along too. So 150y. And I'm left with 60x is equal to 3,000 minus 150y. Okay, remember, I still want to solve for just one value of x, so that means I've got to divide everything by 60, everything, this whole thing. And I'm left with what? Well, 60 divided by 60, we know what that is. That is going to be 1x. And that's equal to 3,000 divided by 60 is 50. Again, I'm using a calculator. Minus, And now I've got 150 divided by 60 is 2.5 y. So what this means is, if I wanted to know the number of small boxes, I've got a really simplified equation to use. I'm going to plug in y, I'm going to multiply it by 2.5, and I'm going to take that away for 50. Simple, easy. I don't have to come up here and multiply and move things. I've got more of a, this is much more efficient. More efficient. Okay, well, now I'm saying, instead of solving for x for the small, what happens if we want to find out the number of large boxes? So I can do the exact same thing by solving for y. So I'm going to go through the exact same exercise. I'm going to take 60x plus 150y is equal to 3,000. I always rewrite my equation. And remember, this time I'm going to solve for y, so I'm going to subtract 60x from both sides. When I do that, I have 150y is equal to 3,000 minus 60x. Okay, remember, I need to solve for one value of y. So now what I'm going to do is I'm going to divide everything by 150. And remember, I got to divide everything by 150. And look what I've got. I've got y is equal to, and 3,000 divided by 150 is, I believe it's 20. I want to just double check. 20. Absolutely. And now I've got to do some simplifying right here. Well, I know I'm going to subtract. I know I'm going to have an x. And now I've got to do some simplification. So the very first thing I'm going to do is I'm going to divide by 10, which leaves me with 6 over 15. And then I'm going to simplify further by dividing 6 and 15 by 3, which leaves me with a final equation of 20 is equal to 20, y is equal to 20 minus 2/5 x. So what this means is, if I want to find the number of large boxes, remember, go back to my original equation had to do with large and small boxes. If I want to get the number of small boxes, I solve for x. If I want to know the number of large boxes, I solve for y. So going back here, if I want to just know x is going to be 50 minus 2.5y. And here, I know that the number of large boxes is going to be 20, and I'm going to subtract 2/5 of x. So I'm going to take the value of x and take 2/5 of it. And then I'm going to take that value and subtract it from 20. So what did we do today? We manipulated equations. Which variable did I solve for? Okay, x or y. Do I have to? Do I have to solve for a variable of x or y? No, you don't have to. Sometimes it depends. It depends on what I'm being asked. So it is efficient. Okay? What else did I do? I found out about equivalency and relationships that work. And I found out about what kind of moves. I'm looking for my other handout here. I reviewed about moves that I can make to make things equivalent. And the last thing is, I learned that, hey, I could have two types of solutions. In addition to solving for one value, I could have no solution, and I can have a value where x is equal to 0. That's okay. So that's what we covered today, Monday. There was a homework assignment that went along with it. Tomorrow we are going to combine two other lessons, and it's going to be on connecting equations and graphs. So hopefully you're back at school tomorrow.